Electrostatics, Coulomb's law. In this chapter, we are going to discuss about two main topics, which is Coulomb's law and electric field, which we studied last year. So let's go through it and revise everything from grade 11. So when you have two charges, let's say there is a positive charge and a positive charge, there is a force of repulsion. If there is a positive and negative, there is a force of attraction. If there is a negative and negative, also there is a force of repulsion. So to calculate the charge between to calculate the force between two charges, we are using Coulomb's law. So when you consider two charges, let's say this is a positive charge Q1 and a negative charge Q2. So there is obviously a force of attraction, right? So how do we calculate this force? According to Coulomb's law, the force, electrostatic force between two charges is directly proportional to the product of the magnitude of the charges. Product of magnitude. Product is Q1 times Q2. And it's inversely proportional to, inversely proportional means 1 over distance between, so let's say the distance between these two is r, so square of distance between them, so it's f proportional to 1 over r square. So that means f is proportional to q1 q2 over r square, or f is equal to k q1 q2 over r square. Okay, so that is Coulomb's law. Force F is equal to K Q1 Q2 over R square. So let's have a look at an example. Let's say there are two charges. Okay, one is positive and the other one is also positive. Okay, right. So these two charges are separated by a distance of 3 millimeters. Okay, and this is 6 NC and this is 2 NC. 2 NC, right? So we want to calculate what is the force. It's very easy, right? So when you look at the first charge Q1 is equal to 6 NC. Charge is expressed in coulombs. So if you see nanocoulomb, 6 times 10 to the power of minus 9 coulomb. I hope you still remember those rules of how to change, right? So if it is MC, 10 to the power of minus 3C, mu C 10 to the power of minus 6C, NC 10 to the power of minus 9C, and PC is 10 to the power of minus 12C. Okay, so we have to change that first. Q2 is equal to 2NC, which is 2 times 10 to the power of minus 9C. Okay, distance R is 3 millimeters. Distance must be in meters, divide by 1000. So it becomes 0,003 meters. Okay, so then write the equation. F is equal to K Q1 Q2 over R square. Substitute the values. K is a constant. 9 times 10 to the power of 9. Q1 is 6 times 10 to the power of minus 9. Q2 is 2 times 10 to the power of minus 9 over R is 0,003 the whole square. That gives you the answer in newtons. Okay, so this is Coulomb's law. How do we calculate Coulomb's law? Using Coulomb's law you can calculate force. So if, let's say, if one is negative, let's say this is negative, when you substitute, we don't include negative sign. Remember that name. We said what? The product of magnitude. So we only need the values. Okay, so do not substitute the signs when you are substituting for the charges. Remember that. Okay, right. Now if it is more than two charges, how do we calculate it? Let's have a look at it. So when you get questions like this, you have three charges now. If they ask you to calculate what is the net force acting on Q2, so always remember your preference is what? Q2. Okay, so preference is Q2. And then when you look at Q2, okay, Q1 is positive, Q2 is positive, Q3 is negative. So let's have a look at what type of force is acting on Q2. So there are two forces acting. One is the force between 2 and 1. Then the other one is the force between Q2 and Q3. Okay. So when you look at Q2, like I said, your preference is Q2. So when you look at Q2, so there is a force between 2 and 1, right? Q2 is positive, Q1 is also positive. So that force is a force of repulsion. Q2 is repelled by Q1, right? So that force is towards the right. So we represent it as F21. You understand that? Its repulsion means it's away from. Q2 is moving away from Q1. But when you look at Q2 and Q3, look at your Q2. What type of force is between 2 and 3? Attraction. Means there is a force between 2 and 3 that is towards Q3. Means that is also to the right. So it's F23. Then we know how to calculate F21 and 23 using Coulomb's law. So when you calculate F21, it's going to be KQ1 Q2 again R square. Okay, substitute 9 times 10 to the power of 9. Let me substitute for you. So this is how we substitute. Okay, 9 10 to the power of 9, that's the value of K. Q1 is 2 10 to the power of minus 9. Understand from minus 9 is n nanocoulomb. 1 10 to the power of minus 9 over distance between 1 and 2. What's the distance between 1 and 2? It's 2 centimeters. You change it to meters. And then you will get what? F21. Similarly, you calculate what? F23. Okay, so I calculated F23 as well. Remember, between 2 and 3, you see 3 is minus, but I didn't substitute minus. Do not substitute the signs, you only substitute the values. Okay, so I got these two answers. Now, look at our free body diagram here. Both of them are to the right. So the net force, the total force, electrostatic force acting on Q2 is going to be, since they are both on to the right, we add them, F21 plus F23, and that will give you the answer, that is 4 comma 5 10 to the power of minus 5 plus 1 comma 69 10 to the power of minus 5, and that answer is 6 comma 19 times 10 to the power of minus 5 newtons. Okay, and then so this is the magnitude. Now if you want the direction, look at it, these two are to the right. Okay, so since both of them are to the right, the resultant is also to the right. Okay, so the answer is right. So this is how we calculate electrostatic force if you have 3 charges and that's in 1 dimension. Coulomb's law 2 dimension. So if you get questions like 3 charges Q1, Q2, Q3. You see Q1, Q2, Q3. Now you can see it is 2 dimension because they are not straight line. It's Q2 and Q3. It's like X direction, and Q1 and Q2, when you look at it, it's like Y direction. So if you have 2 dimension like this, usually the question is to calculate what is the force acting, the total force acting on Q2, the one in the middle. Okay, so that's how the question is coming for you. So same way that we discuss the 1 dimension, you must consider Q2 and see how many forces are acting. So there is a force between Q2 and Q1, correct, and a force between Q2 and Q3. So let's identify the direction. So this is our Q2, right? So the force between 1 and 2, so focus is on 2, so you have to focus at Q2. Okay, right. So when you look at Q2, the force is force of repulsion. So Q2 is moving away from Q1, so that force is downward. So it's force between 2 and 1. Now let's look at Q2 and Q3. So focus is again at Q2, right? So the force between 2 and 3, it's again force of repulsion. Q2 is moving away from Q3, so the force is to the left. So when you look at the diagram now, it is to X and Y direction. So if you use the tail to tail method, you know this is the resultant force, like we studied this last year, right? So this is the resultant force. So we know how to calculate F21 and F23, right? And then from there you can calculate Fr. So I hope you still remember that. Or if you are connecting it like, okay, F23 is this one, right? Then F21 is the second one. Then the resultant is this one, which is Fr. Then you use what? Pythagoras. So same thing. This is tail to head method and this is tail to tail method. Okay. So we use Pythagoras to calculate Fr. So let me calculate for you first. Okay. So this is how I calculated F21 and F23. So this calculation is same, right? And then now Fr, the resultant force, okay? Fr is equal to, according to Pythagoras, you know this is equal to what? The square root of Fx square plus Fy square, right? So when you look at our context now, Fx is F23 square plus F21 square. Then substitute the values and you will get your answer. Okay. So this is the final answer, 3,39 times 10 to the power of minus 5. So this answer is the magnitude. Okay. So that means we need direction, right? For getting the direction, for 2 dimension, we always go for angle theta. Okay. For this diagram, this is the angle theta. Okay. So for this angle, you can see this is the opposite side and this is the adjacent side, right? So we use what? Tan theta. Okay. So when you use tan theta, okay, tan theta is equal to Fx, Fy over Fx, because this is how our triangle is, isn't it so? So this was our Fy and this is the Fx. So this is theta, right? So opposite over adjacent, or theta is equal to tan inverse y over x. Okay. So then substitute for our case. It's going to be tan inverse y is 2,1 and x is 2,3. Okay. So F21 over F23. Okay. And substitute and get the answer. Okay. So this is the answer for theta. Okay. So when you write the final answer, if it is the net force, then it's going to be F net or Fe. Okay. Electrostatic force is represented by Fe, right? What was our answer? 3,39 10 to the power of minus 5. 3,39 times 10 to the power of minus 5 newtons. 83,78 degrees. You see this angle is below the positive negative. This is the negative x-axis, right? So we can say 83,78 degree, 78 degree below negative x-axis. So this is how you can calculate the resultant force in 2 dimension. Okay, so you first identify the forces, identify their directions, and then you calculate the forces separately. Then use Pythagoras to calculate the magnitude. And after that, if the question is not demanding magnitude only, so you have to go for theta to get your direction. So this step is for the direction. Okay, so calculate theta using tan inverse y over x, and then you are getting this angle theta, right? So this angle theta is the one you are getting. So that angle is always to the x-axis. Either it is negative or positive. So for this diagram or for this example, it is to the negative x-axis. So it is below the negative x-axis. That's why we electric field. So consider a charge that can be positive or negative. Okay. So if you place another charge next to this, okay, let's say I put another charge here, Q1, it can also be positive or negative, right? So there is a force that this charge is going to experience, right? But if you place it away from this charge Q, the Q1 is away from Q, you know, as distance increases, you can see the force is going to be less. The force experienced is going to be less and less and less, right? So until what region you can experience that force. That is what you call it as electric field. So we define electric field as a region of space in which an electric charge experiences a force. Okay, a region of space in which an electric charge experiences a force. So you can't call the space around a charge just as electric field. Where it experiences a force, that's where that force can be attraction or repulsion. That region is called what? Electric field. Okay, so this electric field, how do you represent electric field? So electric field you can represent by electric field lines. Okay, electric field lines. Electric field lines. Okay, right. So they normally ask you to draw the electric field lines if it is for a point charge. Point charge means just a positive charge or a negative charge. In this case, it's you can always shape is one criteria, then the direction is the second criteria, and then lines must not touch each other. That's another criteria. We will also check whether the lines are starting from the circle. Okay, because the circle represents this point. This is the charge, right? So all the lines must touch that point. So this is the shape of a point charge. If it's positive, the direction is always from positive to what? To negative. Okay, so from positive means the arrows must be outwards like this one. Okay, so this shows the electric field due to a positive charge. So if it is a negative charge, same shape, just a separate negative charge. Okay, same shape, right? But what is the difference is the direction. So it is to the negative charge, right? So you can use a ruler here when it is charged like this. So to means towards, like towards the negative. So that's a case of a point charge. Okay, so when you draw, lines must not touch each other. Lines must start from this circular region. Shape is important, yeah, and then the direction is also important. But if you have two charges, okay, like for example, there is a positive charge and another positive charge. Okay, so what type of a force is existing between positive and positive is repulsion. So the lines are repelling. Lines are repelling means the line from one positive will not touch the other one. Okay, so shape is important. Let me just show you. So when you draw from, let's say from here, it's up. This central region is important. Okay, that shows the shape because the lines are moving away from each other. Can you see that? Okay, so this one is a straight line always. Okay, then the other lines are curved. You see, like this one. Okay, you know, do not draw so many lines to confuse or to make it to what do you call to touch each other, right? So when you draw few lines so that everything is going to be easy for you. So this is the second one. Okay, we can also draw, sorry, we can also draw one more from here if you want. Okay, like from here, another curve. So if you are drawing a shape, draw it every side so that you know, yeah, freehand drawing. Okay, right. And then we said what direction is from positive, so all the arrows must be outwards. So if it is between two negative charges, what will happen? Same shape, arrows must be inwards. That's the only difference. Okay, right. But if it is a positive and negative, what happens to positive and negative? They attract each other, right? So when they attract, lines are moving from one charge to another charge, right? From positive to negative. You know it. I am just reminding you. Then you can just draw one curve here, another one here, another curve, another, oh, sorry, yeah, I think not like this one is wrong. Okay, yeah, so if you want you can add one more, otherwise the central line is normally straight. Okay, and then from positive to negative, this is positive, so from positive to negative, you see, be careful. Okay, so if you are adding more lines, no problem, but lines mustn't touch each other. That's very important. Otherwise, this is how the shape is going to be. Okay, right, so this is the way you can draw what? Electric field lines. Okay, now when it comes to electric field calculation, right? So they can also ask you to define electric field at a point. Electric field at a point. Okay, so electric field is represented by the letter E. Okay, right, so let's say there is a charge Q. Okay, so let's say this is the point P, any letter, we can use any letter. From the charge to the point, the distance is, let's say, R, or you can use small letter D as well, right? So what is electric field at this point? So at this point there is an electric field from this charge. Okay, so if you define that electric field, for that we always consider there is a unit, there is a test charge, that's a unit positive charge. That's how we are considering. Okay, it's just a point, but we consider that there is a unit positive charge, so we call it as test charge. Okay, so the electric field at this point P is actually defined as the electrostatic force experienced per unit positive charge placed at that point. Electrostatic force experienced per unit positive charge placed at that point. So you can see electrostatic force, it's Fe, experienced per unit positive charge placed at that point. Okay, so E is equal to F over Q. So this is how we use the equation. So using this, E is equal to F over Q. This is the basic equation. So the unit of electric field is, what is the unit of force? Newtons. What's the unit of charge? Coulomb. So electric field unit is Newton per Coulomb. Okay, NC to the power of minus 1. Okay, so that is the unit of electric field. And it's a vector quantity, because force is a vector quantity, so electric field is also a vector quantity. Now, there is one more equation. I don't want to show you how it comes, but you can also calculate electric field using E is equal to KQ over R square. So if distance is given, we always go for this equation is equal to KQ over R square. Here also, when you substitute the value of Q, do not include the sign. If it's negative, you just take the value only and calculate it. From there, we will look for the direction. Okay, so this is how I can explain electric field at a point. So you have two definitions. If they ask you define electric field, you go for a region of space in which an electric charge experiences a force. But if they ask you what is electric field at a point, then it is defined as the electrostatic force experienced per unit positive charge placed at that point. And unit of electric field is Newton per Coulomb. Two equations to calculate electric field. E is equal to F over Q and E is equal to KQ over R square. K is Coulomb's constant, 10 to the power 9 times 10 to the power of 9. R is the distance, it must be in meters. Calculating electric field, I told you have two equations. E is equal to F over Q and E is equal to kq over r square. Okay, so depending on the situation, you choose which one. Okay, so if force and charges are given, then we go for E is equal to F over Q, right? But if distance is given, usually we go for E is equal to kq over r square. So when it is one charge, it's very easy, you just substitute. But if you have two charges, let's say you have q1 and q2. Okay, so q1 is plus 3 nc and q2 is minus 4 nc. Okay, so there is a point x, right, which is 20 centimeters from q1 and 30 centimeters from q2. Okay, so then the question is, what is the electric field at x? So I told you that the point is always positive, because according to the definition, electrostatic force experienced per unit positive charge placed at that point. So always the point is positive. So you consider the point as positive all the time. Okay, so let's say this is our point. I'm just drawing it just below that. So this point is always positive. Concentrate, focus is on point. Okay, so that point and q1, you can see that is a force of what? So if this is a positive charge and q1 is also positive, so point is repelled by q1, right? Because positive and positive is repulsion. So point is repelled means moving away from q1. So moving away means to the right. So I am representing it as E1. Electric field due to q1 is E1. Okay, now let's look at q2. q2 is negative, right? Our point is positive. So positive and negative attraction. So point is attracted to q2. So that means it is towards q2. So that is also to the right. So you see, this is what you need to first do, because the total electric field E is going to be determined by our force diagram, like our diagram, vector diagram like this. Since they are to the same direction, we are going to say E is equal to E1 plus E2. But if one is to the right and one is to the left, it's going to be one minus the other one, right? So since this case, both of them are to the right, we say E1 plus E2. And then now you must calculate E1. Okay, E1 is the electric field due to what? Q1. So E is equal to, since distance is given, we are going for Q1 over R square. Okay, so K is 9 10 to the power of 9. Q1 is 3 times 10 to the power of minus 9 over, distance is 20 centimeters, divide by 100 to get it as meters. So 0,2 the whole square. Okay, so when you calculate this one, you will get 675 Newton per Coulomb. Similarly, you calculate E2. E2 is equal to what? kq2 over r square, which is 9 10 to the power of 9 times, it's minus 4 nc. We don't write minus, we write what? 4 times 10 to the power of minus 9 over 30 centimeters. How do you convert? Divide by 100. So it becomes 0,3 the whole square. And that gives you 400 Newton per Coulomb. So we got E1 and E2. So now how do we calculate E? E is equal to E1 plus E2. E1 is 675 plus E2 is 400. So it is 1075 Newton per Coulomb. Okay, so if it is only for magnitude, you can stop here. But if they say calculate the net electric field, we need direction. What is the direction? Since both of them are to the right, it is also to the right. So this is how we calculate electric field. So the main point is, when you are identifying the direction, your focus is at the point. Okay, if you focus at the point, then you can see that everything is going to be correct. So point, you must consider, is the point attracted or repelled? So then you can easily draw the direction, and always the point is positive. So the point can be between q1 and q2, or somewhere here or here, wherever it is, right? We are going to look at it the same way. Then the direction, the distance, this distance, that you are in substituting. Always the distance is between the point and the charge. So wherever the point is, the distance is between the point and that corresponding charge. So sometimes we need to add to get the distance. So add it. Those are the things that you need to consider when it comes for calculation. And you don't have two-dimensional calculation. We only have one dimension. So then this is how you can solve the one-dimensional question. Okay.